In section 4, we're going to discuss strategies to solve linear systems, and in this video, we're going to start with the direct methods. Let me remind you of what is LU decomposition. So if you consider a matrix A, which is non-singular, then A will have a LU decomposition if there exists a lower triangular matrix L with 1 on the diagonal and an upper triangular matrix U, such that A can be set equal to L times U. Usually you do this by working with the Gaussian elimination. So that is a method that you know and that you used quite a few times to actually solve linear systems up to now. Now, if you're not familiar with this method, I believe you are, but if you're not for some reason, if you want to have a refresher course on it, then I strongly suggest that you watch the wonderful video by Gilbert Strang on this matter, and here is a short link to get to it. Now, there are pros and cons to this method. First, let's start with the pros. It's very useful when you want to solve AX equal B for different B's. The reason is that when you actually have decomposed A into L times U, you've done this once, and that you do this independently on B, completely independently of B. And then when you want to solve AX equals B, then you do LUX equals B. So what you do is first Ly equals B, and then UX equals Y. You see? But what's difficult is not so much solving these two systems, because now they're triangular. So basically what you do is a loop. The difficulty is doing the decomposition L times U, but once you have it, solving the system is actually pretty fast. So that is the first pro. The second pro is actually that sparse matrices with a lot of zeros, will stay sparse in the process. And that is really something nice, because if you have matrices with a lot of zeros, obviously you don't want to store all the zeros. So you don't want to start having operations that will completely mess up your sparseness. And so that's another pro for the LU decomposition. There is a major caveat, and that's really the cons, which is kind of a deal breaker here, which is the complexity of the LU decomposition that is Q cube, and that's really way too much for very large matrices. As we said in the introduction, we could do slightly better than Q cube. We could do Q raised to power 2.3 with the latest algorithms. You can actually go down to 2.3. But even then, it's really a very high complexity. So that is a major caveat of this method. I would like to also stress that when I've said so far, we solve the system AX equals B, at no point I inversed A. Maybe I've written in a formula A inverse, but it wasn't a formula. We usually we don't compute the inverse of the matrix. As a matter of fact, let me be a little bit more more firm on this. Do not compute the inverse of A. Don't do it. All right. Now, again, the theorem that basically links the Gaussian elimination and the LU decomposition is here. There exists a LU decomposition if the Gaussian elimination works out, and if it works out, then in this case it is unique. And you see that I put 1 on the diagonal of one of the matrices, so that's why it is unique. Now, if A is a non-singular matrix with coefficients in R that is symmetric, positive, definite, then the LU decomposition is actually a little bit better. L can actually be written as a triangular matrix, B with positive diagonal terms, and U will be the transposed of this matrix. So what you will have is A equals B, B star. That is called the Cholesky decomposition. Finally, let me finish with another decomposition. Every non-singular matrix A can be uniquely decomposed as Q times R, where Q is an orthogonal matrix and R is an upper triangular matrix with positive terms on the diagonal.